Processing coal by drying, grinding, and pulverizing may create conditions conducive to fires and explosions. Until recently, instrumentation often failed to detect the dangerous condition until after the damage was done. Now, KVB, a nationally recognized leader in combustion research and engineering, has developed and produced a fully automated coal fire protection system. It detects and predicts an impending fire and explosion and provides sufficient warning to take corrective action. The KVB Coal Fire Protection System guards against coal fires and explosions before they start. KVB, located in Orange County, California, began as a consulting firm applying engineering solutions to combustion problems in 1970. KVB has grown accordingly to provide engineering consulting in all facets of fossil fuel utilization. Our Irvine headquarters is staffed with experienced researchers and engineering consultants. In our Santa Ana research facility, extensive laboratory developmental testing is performed to find solutions to operational and environmental problems. Our Tustin facility manufactures practical equipment systems designed to implement these solutions.
By 1982, over 50 KVB coal fire protection systems were in operation, protecting more than 250 hazardous locations, along with other KVB instrumentation at more than 200 installations for industrial plants and utilities.
KVB scientists and engineers are nationally recognized contributors to fundamental combustion research. They successfully apply their research knowledge to practical solutions of today's operational problems.
The key to successful combustion control often exists in the understanding of basic combustion processes. Very simply stated, combustion is a very rapid oxidation and energy release. In the molecular oxidation of coal, oxygen combines with carbon and then energy is released, along with other various gases and particulates. In a situation where the energy or heat does not dissipate fast enough, the oxidation process speeds up and spontaneous combustion occurs. In pulverizers, the problem is aggravated because the surface to volume ratio of pulverized coal is far greater than that of the unpulverized coal. Accelerated reaction speeds with the pulverized coal are faster and faster ignition time occurs. The coarse coal will gradually ignite while the pulverized coal ignites instantaneously.
The fuel-air ratio in coal systems commonly passes through the range of 1 gram per liter of air, the mixture most likely to explode with flame front speeds approaching that of dynamite. This combustible mixture of coal and air can exist in the mills and pipes of the air-conveyed coal systems, causing continual danger of fires and explosions. KVB has sought a solution to the problem of coal fires, a problem that has been a continuous threat to safe operation. Fires in pulverizers are not an uncommon occurrence. Most coal-fired power plants find explosions and fires to be a major concern due to risk of injury to operating personnel and the high cost of downtime.
A study on pulverized coal power plant fires and explosions was conducted by Brigham Young University in 1979.
A KVB researcher reports on a portion of this study which surveyed the frequency of these problems in 25 utilities.
The report revealed that explosions consistently occur given an ignition source when the fuel-air mixture is leaner than the normal mill operating condition. The survey noted the frequency at which coal fires occur. Drawn from a sample of 25 utilities, it was found that 7 utilities reported 3 or more major fires per year. 16 utilities had 3 or more minor fires per year. 12 utilities indicated that they had very serious problems.
Coal fires can be extremely detrimental to safety and operational stability, and they're often quite costly. One southwestern utility company has estimated losses of $4,000 per hour of time that one of their pulverizers is out of service. Minor fires cost about $16,000 for 4 hours of downtime, and major fires can exceed $50,000. These figures are based upon fuel differential cost and do not include the cost of cleanup and repair. Heretofore, detection systems have provided little or no warning time and have allowed fires and explosions to develop before corrective action could be taken. One method, that of using temperature sensing devices, such as thermocouples, which may be a part of the existing control system, has proven inadequate as a warning device. Several factors contribute to the ineffectiveness of the thermocouples. First, the necessary shielding that protects the thermocouple from the erosive mill atmosphere also reduces response time.
Second, the thermocouple indications are masked by process control. As the internally generated heat starts to raise the exit temperature, process control reduces the inlet temperature to keep the outlet temperature constant until the fire has raged out of control and the hot air cold air dampers can no longer overcome the self-heating inside the pulverizer.
As we already know, the oxidation process releases gases and particulates as well as the energy that thermocouples attempt to measure. Both carbon dioxide, CO2, and carbon monoxide, CO, are products of coal oxidation. Of these two, carbon monoxide is proven to be the most sensitive indicator of oxidation. This knowledge provides the key to the KVB coal fire protection system.
A simple demonstration will show the difference in sensitivity to oxidation between a thermocouple and the KVB coal fire protection system. We can create a condition of spontaneous combustion similar to that which may take place in a mill when the flow of air and coal is interrupted, causing coal accumulation and self-heating. Both a thermocouple and a CO probe are placed into this flask that has been heated to a normal mill operating temperature on this hot plate. The thermocouple will detect the change in temperature due to self-heating, while the CO probe will continuously draw a gas sample which will be analyzed for carbon monoxide content. The results will be displayed on this infrared gas analyzer, on this strip chart, and on the CO meter. I will now add some pulverized coal to the flask and compare the response times for each in detecting the resulting spontaneous combustion. After approximately 2 minutes, the first indications of oxidation are visible on the CO analyzer. After approximately 4 minutes, the high CO alarm is showing on the coal fire protection system. After approximately 5 minutes, the temperature is still approximately 163 degrees Fahrenheit, while we're showing approximately 50 parts per million on our CO monitor.
The report examined methods for giving advanced warning of fire or explosion hazards. When comparing temperature monitoring and carbon monoxide monitoring, it was found that carbon monoxide monitoring provided a longer period of time for analysis and corrective action. In the temperature monitoring approach, only minutes elapsed before a confirmed fire or explosion. Whereas in carbon monoxide monitoring, perhaps hours elapsed before this hazard occurred. And in addition to a lengthy warning period, the carbon monoxide monitoring system detected small fires in the system, while the exit temperature monitor did not indicate the presence of a fire.
Research on the carbon monoxide monitoring system began in 1969 in the United Kingdom. The Central Electric Generating Board began experiments to determine a precursor or warning to incipient or barely smoldering fires. They determined that carbon monoxide was an indicator of self-heating and that the carbon monoxide level would be the most important warning for pulverizer fires. In 1972, the British installed their first system in the Cottam Power Station. KVB was alerted to this research in 1973 as it supported their own views and investigations of early warning systems. In 1974, collaboration with the British of a system design began. Successful testing of a prototype system in 1975 confirmed the British findings. The first operational system was installed at Cayuga in 1978 for Public Service Indiana. 2 years of operating experience at PSI found that rising carbon monoxide without corrective action invariably resulted in a fire condition. Conversely, instances of rising carbon monoxide that were responded to promptly resulted in a resumption of normal operation. In all cases, a minimum of 1 hour warning time resulted.
Since the successful installation at Public Service Indiana, KVB has installed over 50 additional coal fire protection systems at major utilities throughout the world. The battle against coal fires and explosions is underway.
The KVB coal fire protection system is fully automated or can be manually controlled as required.
It is designed to monitor up to 12 locations.
The system samples the air in the classifier of each mill sequentially through a probe which filters out particulates. The air is dried and sent to an analyzer for measurement of carbon monoxide. The results are recorded permanently on a strip chart recorder and can be viewed on the carbon monoxide display meter. When the carbon monoxide level exceeds a preset standard, the KVB alarm system is activated. If conventional operation procedures fail to reduce the carbon monoxide level, the system can be programmed to signal a central process controller to alert the mill with steam or water in order to prevent a fire or explosion.
At the Jeffrey Energy Center, St. Mary's, Kansas, a KVB engineer commences to describe the highly beneficial features and functions that make the system an integral part of safely operating coal handling equipment.
The KVB Coal Fire Protection System is a fully automatic, self-calibrating system designed to protect against fires or explosions in coal pulverizing equipment. The computer-controlled sample acquisition, conditioning, and analysis system contains all the improvements and refinements dictated by research and experience spanning 3 decades at hundreds of locations, successfully overcoming the special problems presented by gas sampling in pulverized coal systems. The system's instruments and sample handling components have demonstrated reliable, precise performance. Sample gas from a hazardous location is drawn through a probe tip filter which removes particles larger than 7/10 of a micron. Motorized valves select individual points for sampling and allow back purging and priming. Motive force for the sample is provided by a positive displacement pump, which then delivers pressurized sample gas to the refrigeration condenser for removal of moisture. A conductivity sensor ensures that nothing but dry gas is introduced to the carbon monoxide analyzer. After analysis, the sample gas is vented to atmosphere. The probe assembly is a crucial factor in the success of our system. Its purpose is to allow delivery of particle-free sample gas from a highly particle-laden, erosive environment. Blocking the coal particles is a centered stainless steel filter, which is housed in an erosion shield. The erosion shield is plasma coated by a proprietary process to withstand the erosive mill environment. The ball valve and V-seals allow removal of the probe while the mill is in operation. Erosion shields can perform up to 2 years or more without replacement. The sample is pulled from the probe into the analyzer cabinet, where it is again filtered through a replaceable cartridge filter, which will remove any remaining particles. The filter is easily accessible to simplify cartridge replacement when necessary. The main sample pump and the bypass pump are simple diaphragm pumps for long and continuous operation. The refrigerated condenser chills the gas to remove all moisture above a dew point of 35 degrees Fahrenheit. This ensures that the analyzer sees only clean, dry gas. The conductivity sensor is a fail-safe mechanism. If it detects moisture in the gas stream, it will shut down the sample pump, thereby protecting the analyzer. The analyzer is of non-dispersive infrared design, utilizing the latest technology microflow detector to measure the absorption of infrared energy at the 4-micron wavelength. While completing the sampling cycle and interpreting the results, the computer simultaneously controls the preparation and cleansing of the other probes in line for sampling. This specialized sampling scheme solves critical problems unique to sampling in pulverized coal systems. The computer is programmed to control the sampling selector valves for 1 to 12 hazardous locations. The microprocessor stops the sample gas flow from all probes except the one being analyzed and the one next in line. To assure immediate response time and a fresh sample, the sample gas flow from the probe next in line is vented overboard in preparation for analysis. This technique assures that a fresh sample from each location is always available for analysis, and it reduces lag and transit time to a minimum. To keep the filters and lines clean from coal dust, each probe is automatically purged upon completion of its sampling assignment. Instrument air forces coal particles out of the probe, cleaning it for future sampling. A vacuum switch is activated if clogging should occur. At the control panel, the microprocessor communicates with the operator by contact closures and bright alphanumeric displays. Other configurations are possible. During normal operation, the probe currently being sampled will be indicated in the message display. Real-time results of analysis for this hazardous location are displayed numerically in parts per million. The operator may instantaneously gain manual control over the system by use of control switches, and is kept continuously informed of system response to commands by the bright alphanumeric display. Restoration to automatic control is just as simple. The computer's primary function, however, is to relieve the operator of interpretive duties and exposure to false alarms. On first sensing a rising carbon monoxide level, the computer automatically determines the location of the potential fire and verifies proper system operation, including calibration of the analyzer. Only then does the alarm sound. Permanent records of the carbon monoxide levels of each hazardous location may be recorded on the strip chart recorder.
The computer-controlled system provides low-cost installation and minimum maintenance. The computer has self-diagnostic capabilities for every component and every function. Regular service requires that the line filter elements be checked and changed if necessary. Every 6 to 8 months it is expected that the calibration gas will require replenishment.
Components have demonstrated reliability and low maintenance at installations throughout the country since 1972 and are currently in use in continuous emission monitors installed at many utilities. In addition, KVB warrants for a period of 1 year to correct, either by repair or replacement, any defects due to faulty material or workmanship that develops under normal and proper use.
KVB engineers will assist in installation, supervision, startup, and training. At your request, they will visit your facilities to familiarize your personnel with operational procedures.
Every facility has its own methods for pulverizing coal and dealing with coal fires. Here at KVB, we recognize this and follow up at your request to help your staff design a plan to fit your needs. This pulverizer fire procedure was developed for one of our clients and is very site-specific. The plan is based on a two-tiered level of concern, one at low carbon monoxide levels and one at relatively higher carbon monoxide levels. When the operators are alerted to a high alarm, they perform a visual inspection of the pulverizer to see if there is an inlet air fire taking place. If there is no inlet air fire and there is carbon monoxide coming from the mill, they operate on the presumption that they are approaching an above-the-bowl fire, in which case they place the monitor on the mill continuously and increase the feed to the pulverized coal system. After increasing the feed, they watch to see if the carbon monoxide returns to normal. If it does, they resume normal operation. If not, they reduce the outlet temperature of the mill to see if the carbon monoxide returns to normal. If it does not, they are on alert, and in the presence of a high alarm, they deluge the pulverizer system. These carbon monoxide monitoring procedures offer the operator many more options than would be available in temperature monitoring. In temperature monitoring, a high alarm means that the fire is already out of control, and the operator has no option or choice but to deluge the pulverizer.
Utilities across the world have been using the system with success similar to that of Kansas Power and Light.
In England, 40 plants with 240 pulverizers reported the incidence of fires reduced by 95%. Considering the high cost of coal fires, the system can more than pay for itself by preventing a single fire or explosion. KVB personnel will be most pleased to send you further information or answer any questions you may have regarding the KVB Coal Fire Protection System.